Now we must always find the particle somewhere. So this sets a criterion. That the integral of this differential probability, or dp dx, over x from minus infinity to infinity has to equal 1. But remember that I wrote dp is the norm squared of psi times dx. So if I act like a typical physicist and divide both sides by dx, dp dx equals the norm of psi squared. So this is equivalent to the statement that the absolute value of psi squared dx has to equal 1 at any instant in time, because remember, this is psi of x and t. So it may be true that the spatial probability will change over time, but its integral always has to equal 1. Oftentimes, this has a very useful constraint for us in terms of how to calculate these amplitudes. So if we had some sort of sinusoid like this, or a sum of sinusoids, this places constraints on A, because we know that the integral of this thing squared has to equal 1. So here's a question to consider, just as a practice problem. Suppose we had a particle in a box, an infinitely deep potential well that goes from 0 to L, and this particular particle happens to occupy the ground state wave function, the lowest energy state. What would be the probability of finding it in the first quarter of that box? Classically, you would say, well, it's just bouncing around, so the probability should be about 25%. Quantum mechanically, we won't get that answer, and there's a separate home practice problem video that you can watch just to watch how to do that solution. But I'd like you to try it for yourself using that particular constraint. So if you like, pause this video and watch the second video on that particular practice problem. What I believe you'll find is that this probability is 0.091, which is less than 25%. So it's a somewhat odd solution, or a somewhat surprising solution.